How does the difference between 0.00000000398 and 0.00000000398 cause one to have red eyes after swimming? To answer this, we first need a way of dealing with rather small numbers, or in some cases extremely large numbers. This leads us to the concept of logarithms. Well, what are logarithms? Let's take the base number b and raise it to a power p, like 2 to the third power, and have it equal a number n. We get an exponential equation, b raised to the p power equals n. In our example, that'd be 2 raised to the third power equals 8. The exponent p is said to be the logarithm of the number n. Most of the time, this will be written log base b of the number equals p to the power. This is starting to sound a bit confusing with all the variables. So let's show this with an example. What is the value of log base 10 of 10,000? The same question could be asked using exponents. 10 raised to what power is 10,000? Well, 10 to the fourth is 10,000. So log base 10 of 10,000 must equal 4. This example can also be completed very simply on a scientific calculator. Log base 10 is used so frequently in the sciences that it has the honor of having its own button on most calculators. If the calculator will figure out logs for me, why study them? Just a quick reminder, the log button only computes logarithms of base 10. What if you want to go into computer science and need to understand base 2? So what is log base 2 of 64? In other words, 2 raised to what power is 64? Well, use your fingers. 2, 4, 8, 16, 32, 64. So log base 2 of 64 must equal 6. So what does this have to do with my eyes turning red in some swimming pools and not others? Well, it leads us into an interesting use of logarithms in chemistry, finding the pH of water samples. pH tells us how acidic or basic a sample is and can be calculated with the formula pH equals negative log base 10 of the hydrogen ion concentration, or H+. We can find the pH of water samples with hydrogen ion concentration of 0.00000000398 and 0.00000000398 quickly on a calculator. Punch negative log of each of those numbers, and you'll see the pHs are 7.4 and 8.4. Since the tears in our eyes have a pH of about 7.4, the H+ concentration of 0.70398 will feel nice on your eyes, but the pH of 8.4 will make you feel itchy and red. It's easy to remember logarithms. Log base b of some number n equals p by repeating the base raised to what power equals the number. The base raised to what power equals the number. The base raised to what power equals the number. So now we know logarithms are very powerful when dealing with extremely small or large numbers. Logarithms can even be used instead of eye drops after swimming.
Okay, so the going on page 71, that was a little intro to logs to kind of remind you, because again, they're not brand new to you. Being able to rewrite logs as an exponential equation will help us solve a lot of them. Got to know how to take them in both directions and what they're used for. I'm sure you use them in chemistry for probably stuff like that. You may not have known why you were just pushing buttons because they told you to push buttons, but that's a way we use them to talk about really big numbers or really small numbers. So logarithmic form looks like this. Log base b of a equals x. Now, they were using p and n in the video. It doesn't matter what the variables are. The same thing still happens. But to rewrite it in exponential form, the base of the log is always the base of the exponential. And then so the base raised to that power is equal to that number. It goes around in a little circle. Okay? So b to the x power equals a. So we have to use logs to solve them sometimes when our variables are in the numerator and we have to get them out of the numerator. And we'll look at different ways we're going to handle this. So we have a logarithm. When it has a base 10, it's called the common logarithm. And like it said in that little video, that's the only one that's special enough as far as the regular logs go to have its own button on the calculator. And so it can be written without a base. It's actually supposed to be written without the base. So instead of looking at log base 10 of x, it would just be the log of x. Okay? So we're not going to need the calculator at the beginning because the first thing we're doing is just converting. We're just rewriting. This is where you want to make sure you're actually reading directions because sometimes you try and do too much. All it says is to write it in exponential form. So we have it in log form. To rewrite it, 7 is my base. So 7 to this power equals 49. And that's it. There's nothing to solve, first of all, because it doesn't say to solve it. It says to write it, and we did, and we're done. Okay? So then, number 2, we would take 2, which is our base, to the 5th power, and that has to equal 32. Make sense? What's our base in number 3? 10. So this would be 10 to the 3rd equals 1,000. Okay? Go ahead and do 4 through 6. And then make sure you agree with me. Yes. And then let's just talk a little bit about these exponents and how we could write them differently. When you have a negative in an exponent, what does the negative do? Makes it the reciprocal, okay? So this 4 to the 3rd would be 1 over 4 to the 3rd, and then 4 to the 3rd is 64. So that negative means if it's in the numerator, it goes to the denominator and vice versa because it's the reciprocal. What's another way to write 8 to the 1/3 power? What are the rational exponents, the little fractional exponents do? So 8 to the 1/3 power cube root. It's the same thing as the cube root of 8, right? Same thing, because the cube root of 8 is 2. Does that make sense to you? All right, and then so on number 6, another way to write that 9 to the 3/2 power, well, 3 is cubing the 9. The 1/2 is, what would just be 9 to the 1/2 power? Just 9 to the 1/2. Like how would I? I'm sorry. Let me ask that differently. How would I write 9 to the 1/2? Like I don't want to know what the answer is. How else could just here? I could rewrite this as this. So if this was 9 to just the 1/2, forget the 3 for a second. Square root. Okay. So this is the 1/2 gives me the square root of 9, and that 3 is 9 cubed. So that's another way to write it. We're leaving it like this, but just you need to remember these things. And then these two things I could do in either order. It would be easier to take the square root of 9 and then cube it, which would give you 27 in the end, of course. But all right, so just a little reminder about exponents there. All right, so that's taking logs, rewriting them in exponential form. So now we're going to take the exponentials and rewrite them in log form. So here, the base of the exponent, or the base of the exponential is 5. So this becomes log base 5 of what? 25 equals 2. So 5 log base 5 of 25 equals 2. You go around the little circle again. So here, log base what? 8 of 1 equals 0. And then this would be log base what? 3 of 1 over 81 equals negative. All right, write the next 3 out on your own. Do you need more? All right, so this would be log base 12 of 2 times the square root of 3 equals 1/2. Yes? Log, and then I wouldn't write a base because it's base 10, so the log of 1/10 is equal to negative 1. And then here, log base 16 of 8 equals 3/4. Okay? Everybody okay with all that? Yes? All right, so now we're going to do the next few. Again, we don't even need the calculator yet. We're going to need it in a little bit. But we're going to evaluate these. Nobody expects you to just like know them, right? But you need to be able to rewrite them as exponentials. Did anybody have any questions about those? Okay, we're going to rewrite them as exponentials and then go from there. So that means I need to introduce a variable. I'm going to say this equals x because I'm evaluating, which means I got to get an answer. So I'll put a variable in there. So to rewrite it as an exponential, this is going to give me 6 to the x power equals 36. We agree with that? So now what we're going to do is we're going to get common bases. right? So on the left, I have 6 as the base of my exponential. This I can change into a 6. So this gives me 6 to the x equals 6. And how do I get 36? It would be 6 what? Squared. Okay? 6 times 6 would be 6 squared. So now that I have common bases, what this tells me right here is that x has to equal 2. Right? Does that look familiar? That's your answer. X equals 2. Or really, log base 6 of 36 equals 2, but that's fine. We don't have a lot of room there. So when I rewrite this, I'm going to set this equal to x. That means 2 to the x power equals 128. You have to decide what your common base is going to be. It's not always the one that's with the variable. It is in this case, but just know that it's not necessarily always that one. So I'm going to have 2 to the x equals 2, and then I got to figure out what that exponent's going to be. So 2 times 2 is 4, times 2 is 8, times 2 is 16, 32, 64, 128, 2 to the 7th. So x equals 7. Okay? And you would be expected to be able to do that without a calculator in front of you, because there will be calculator and non-calculator sections of stuff. All right, so I want you to do 15. Without a calculator, put that down. So when I rewrite it, what's my base? 10. So this is 10 to the x power equals 1 over 100. So that's step 1. Then I have to decide what my base is going to be. I think I'm going to go with 10. So 10 to the x equals, so this will be 10 to something. How do I get it in the numerator? A negative, right? And then so 100 to the negative 1 power is the same as 1 over 100. And then to get to 100 from 10, it's squared. So it'd be negative 2. That means that x equals negative 2, and I'm done. Easy enough? Any questions? All right, so let's rewrite number 16. This is going to set that equal to x, so that'll be 16 to the x power equals 2. All right, so again, I'm not always going to use what's with my variable as my base. I don't want the common base to be 16. The common base here is going to be 2. So instead of 16, this is going to be 2. Well, 2 to what power is 16? 4, right? 2 times 2 is 4, times 2 is 8, times 2 is 16. So this is going to be 4, but I still have that x there. So it's 2 to the 4x is the same thing as 16 to the x power. That's equal to 2 to the first power, right? So now that my bases are the same, I know that 4x has to equal 1. So what does x equal? 1/4. Okay. Everybody okay with that? Any questions at all? All right. Let's look at 17. Going to have, let's set that equal to x. So 3 to the x power equals 1 over 27. So I think I'm going to go with 3 for my base, right? So that'll still just be 3 to the x power equals 3. Now, since this was in the denominator, I know that's going to be negative, right? And then 3 to what power gives me 27? Negative 3. Okay, so this will be negative 3. So that means that x equals negative 3. All right, so go ahead and rewrite 18 as an exponential. So we get 8 to the x power equals 1. Now we need a common base. My common base can't be 1 because 1 to any power is going to be 1, which means my common base could be 2 or it could be 8. I think I'll go with 8. So if I'm going to leave this as 8 to the x power, then that has to be 8 to some power. What power would that be? 0. Anything to the 0 power except 0 is 1. So 8 to the 0 power does equal 1, right? See how you have your common bases there now? That means that x equals 0. So the log of any base of 1 is going to be 0 every time, because when you rewrite it as an exponential, whatever that base is to the 0 power is going to give you 1 every single time. Okay, that's going to be one of our properties that we look at in a minute. Everybody good so far? All right, so then we have the change of base formula, because not all of them can be rewritten like this. Like these all are rewritten and the numbers work out just fine, but if you look at number 19, we would have 5 to the x power equals 34. Well, I can't take 5 to any power that I just know of to get 34. It would be some weird decimal or whatever. So instead, I'm going to have to change the base, right? So it says some logarithms are not as easy to evaluate as those above and will require the change of base formula. So whatever this is, log base, whatever the base is of a, it's going to be the same as log of a over log of b. Oh, that looks like a base. And that's log base 10. That's why we're not writing it on there, because I can't do a log base 5 on that calculator. I can only do log base 10 or natural log. And to remember how this goes, the base is the one that's on the bottom. Okay, so it's pretty easy to remember how to split it up. So it says approximate each logarithm with using the change of base formula. So the first thing I have to do is rewrite this. So log base 5 of 34 is the same as log of 34 over the log of 5. And again, on this one, that's not something that you're expected to just know those. This is when you would actually use the calculator to approximate it. And you can type them in just like that. Just make sure that you're paying attention to your parentheses. So everybody type that in to find your log button. Did you see it? Everybody see it? And then how many decimal places should we go to? 3. All right, so Robert, you want to give me what you got? Oh, I said, can everybody find it? Yes. Good, so 2.191. Yes, so just make sure everybody got that. Okay. You don't have to close the very last one most of the time, but the in-between one, yes, that would be important. Okay. That's probably why. Yes, you have to close that. So then, number 20, I've got log base 2 of 98. That's going to be the log of 98 over the log of 2. Oh, I keep putting that as a base. Okay, and then you just type that in. So go ahead and do that one, and then go ahead and do the next 4 as well. All right, Hector, what'd you get for 20? 6.614? Y'all agree with that? No? Why not? It's 6.615. So if you probably don't have that number sitting and looking at you in the calculator anymore. So I don't remember what came after that. But it was a 7? Okay. So if I get 6.6147 like that, that 7 rounds that 4 up to a 5. So careful with your rounding, because on the AP exam, or really on anything anybody grades, it has to be accurate to 3 decimal places. So even if you know what you're doing 100%, you did all the hard stuff correct, you may not get credit for that number if it isn't correct to 3 decimal places. So that's a common thing to happen. All right, Juan, give me what you got for 21. Okay, good. Y'all agree with that? Yes? Okay, and you can put the 0 first. I don't ever write those, but it's fine to write them. It's fine. All right. So 22. Michael Rodriguez, what did you get for 22? Okay. Y'all agree with that? Yes? Okay, good. All right. Then, Zainab, what did you get for 23? Okay, 4.930. Y'all agree with that? Yeah. Okay, and I'm not sure, does anybody know what the calculator actually said? 92999. Okay, so thank you. So it's 4.9299 and then something. So that 0 there is important, though. That's what I wanted to make sure we talked about again. Because if I just put 0.93, that tells me that it's exactly 0.93. That 0 there tells me that there was more out there. Just like if with money, if you get, it's $20.40, they don't say it's 20.4, like it's 20.40 because it's to the nearest penny, or whatever. So Same thing here, 3 decimal places. But if you do get like 1.25 and that's exactly what you get, then you do just put 2 decimal places. Does that make sense? So that's tells you something different. Okay, good deal. Then Michael Gutierrez, what'd you get for 24? Okay. Now, when you got this in your calculator, do y'all agree with that? Okay. And it kept going, right? So that wasn't around or whatever. So do you know what this is as a fraction? Yeah, so it's negative 1/3. So, and I didn't say this ahead of time, so I didn't expect you necessarily to write it. But when you can get a more accurate answer, which this is a more accurate answer than that, then we would want to write it that way. You may not always recognize all of them, but that's something we want to try and get at. Okay, everybody good so far? Yes? All right, good deal. All right, so then we talk about a natural logarithm. That's where the e comes into play, right? So if I have a log, anybody have any questions? Oh my goodness, we're all good on those, right? A logarithm with base e is called a natural logarithm. So log base e of x, we don't really ever write it like that. Instead, it's the natural log of x. So ln, meaning natural log. And so you make sure you can find that button on your calculator. If you found e yesterday, you can find natural log today, or whenever we did it. It says write each equation in exponential form. So we're not actually touching the calculator on these. We're just rewriting them. So the base here is e, even though we don't see it, just like it was for just a regular log. So this is e to what power? The 4th. E to the 4th equals x. So for 26, it would be e to the what? X equals 10. Then for 27, we're going to write them in log form. So this is log base e, which is just the natural log of 50 equals what? Is that an x? I can't tell. X. Okay. Up here, the tiny ones, they just look like blobs. I can't tell what it is. Then this would be natural log of what? X equals 0.5. So you just got to make sure you can put the exponents in the correct places. That you're going around the little circle there. All right, so then there's no change of base formula because the base is all the same for natural logs. So these two are really just punching buttons on the calculator. So if you just punch the buttons, make sure you can find the natural log key. It's also good to have these kind of things in your notes when you want to make sure you have if you have a calculator you're not very familiar with, to make sure you're punching the buttons right in case you have to do things backwards. So just type these in. Robert, what'd you get for 29? 4.159. You'll agree with that? Yes? That should be rounded. What does the calculator say? 159 what? Oh, it said, did it say 588? What was it? Okay, so yeah, so that's how you round, you look at the 4th one. Does that make sense? Okay. And then, Jose, what'd you get for 30? Okay, you'll agree with that? Yes. Okay, good deal. All right, everybody good with all that? Awesome. So that's going to be the extent of the assignment today, but we are going to go ahead and fill in the reference sheet, which has some of these things on it we've talked about today, but then it'll lead us into tomorrow as well. So if you will grab your little pink sheet, and let's see that. Oh, I didn't clear that off. All right. So this is going on whatever the next page is. I don't even know. 72. That sounds good. So you can write 72 at the top up there. So this is going to be a good reference sheet for all your different log rules. Common logarithm, base 10 is written as just log of x. Natural logarithm, base e is just the natural log of x. Okay. So some basic properties that you have here. Log base b, no matter what the base is, of 1 is going to equal the same thing for all of the bases. What do you think that is? 0 or 1? Think about what it would be in exponential form. This would be b to the x equals 1. So what? It would have to be 0. So anytime you take the log of 1, you're going to get 0. Okay. Then what do you think log base b of b is going to give you? 1, because this would be b to the x power equals b. That means the power would have to be 1, right? So if you take, if the argument and the base agree are the same, then it's 1. If this is 1, then it's 0. Okay? And that's going to come in handy a lot, what we do. So log base 6 of 1 would have to be what? What's log? 0, because the log of 1 is 0. Log base 4 of 4 would have to be 1. Okay, see how easy those are? So then we have a product property, which means that we're taking the log of two things that are being multiplied. All right? It's not two logs being multiplied together, it's the log of two things that are being multiplied, right? So then I can split those up, and those split up into addition. So this becomes log base b of m plus log base b of n. And it works in both directions. I can take two things that are being multiplied and split it into adding two separate logs. Or if I have two separate logs being added with the same base, then I can condense them into something that looks like that. So you got to be able to go condensing and expanding. So if you look here, now again, the bases of the logs have to be the same. So these are the same. Since I'm adding them, same base, that means I'm going to end up with log base 3 of 8 times 3x. I get to multiply those two things together. And then I can simplify that a little bit. This becomes log base 3 of 24x. Okay. Everybody okay with that? Then I'm going to need to be able to expand them as well. Well, I have the natural log. Well, this works with logs or natural logs, but I've got the natural log of these three things that are being subtracted. Now, if something's being subtracted or added in here, I can't do anything with it. If it's being multiplied is what I'm looking for. There's no multiplication going on here. Do you think I could adjust that where it does become something with multiplication? What could I do there? Factor it. So I can factor this. This becomes the natural log of, I'm going to put little brackets here. I got these two, I'm going to factor it into two binomials, right? So this would be x minus what? 2 and x plus 1. So now I have the natural log of this being multiplied by that. There are my two things that are being multiplied. This is my m, this is my n. So then I can split it up, and it becomes the natural log of x minus 2. Those parentheses right there are super important, because if I don't put them, it's going to look like the natural log of x, and then subtracting 2, which is something different. Then plus the natural log of x plus 1. Any questions at this point? All right. So then I have a quotient property. If multiplication turns into addition, then division turns into what? Subtraction. So log base b of m divided by n would just be log base b of m minus log base b of n. And again, you have to be able to go in both directions. So I'm going to condense it, meaning I already have subtraction, same base. In this case, it's base 10. So this gives me log of 80 divided by 16, because that subtraction turns into division in one log. And then I can simplify that. What's 80 divided by 16? 5. Log of 5. Then to expand it, I go in the other direction. So I have log base 2 of x over 5. That's going to give me log base 2 of x minus log base 2 of 5. There you go. So notice there's a product property and a quotient property. There's no addition and subtraction property. Okay, so if I'm adding or subtracting something like this, like I can't do anything else with these properties. It doesn't work that way. All right, so then I have a power property. I've got log base b of m to the n power. So this exponent here comes out in front over here. So this becomes n times the log base b of m. And again, that can go in both directions there. Yes, sir?
For the quotient property,
Mm-hmm.
you have to put the impulse on that one, and for the other one, it doesn't matter, right? Because you're just adding them.
Right, for the other one it doesn't matter because you can multiply and add in any order. Yeah. But on this one, yeah, this here, the order definitely matters because the negative part is the denominator. So I've got n times the log base b of m, and we're going to condense this, which means if I have a number or anything being multiplied by a log, that this can come up and become the exponent. So this can become the natural log of 9 to the third power. And then what is 9 to the third power? What? Oh, I thought you said something else. 729. Okay. And if you think about it, it's not that bad. 9 times 9 is 81. 81 times 9, well, 9 times 80 is 720, and then 9 times 1 is 9. So there's your answer right there. All right. So then I have log base 7 of 3 to the 2x power, or 3 to the 2x power. So this is my exponent. It gets to come out in front, and so I get 2x times log base 7 of 3. And that's the best I can do there. Okay. All right. Everybody good? All right, and then the change of base, we've already talked about change of base, but again, this kind of puts everything together. So log base b of a is going to be equal to, what would the numerator look like? Log of a over log of b. Good. Yeah, that way they're both in base 10. So then go ahead and rewrite and actually evaluate these on the calculator. You can do that while I hand out your homework. No, you can have it. Your brain goes. Eduardo, can you tell me what you got for the first one? 0.327 here? Okay, do y'all agree with that? 0.327? Yes? Okay. So do you have written down what I have written down? Oh, you did it upside down. The base goes on the bottom. That's what happened. Okay. That's okay. So just in case you did the same thing, he had log base 5 on the top, and that's okay. So what did you get then? 0.061. Yeah. So make sure that's actually what you get there, Eduardo. And then for this last one, you'll just tell me, what do we get? 0.263. Okay, does everybody agree with that? Yes, so make sure you're actually getting these numbers. Don't just take my word for it and write them down, because you want to make sure you're typing them in right. Any questions at all? All right, so go ahead and get these glued or taped in now.